a lot. I lived for 3 years in Europe as a grad student and missed all of television from 92 to 95. And then was a postdoc and didn't have time to watch television. And so I've got like a whole decade of the 90s. People talk about television shows in the 90s. I'm like, I got no clue. Yeah. All right. Eureka.
Here.
Bren. Down here. She's taking a note. Laurel.
Here.
Carly. Kelly.
Here.
Joe. Dakota.
Here.
Anna Good.
Here.
Carrie. Robert.
Here.
Diamond.
Here.
Marjwan. Dylan.
Yeah.
Tanisha.
Here.
Maisie.
Here.
Anna Mae.
Here.
Justin.
Here.
Emily.
Here.
Caitlin.
Here.
Chelsea. Bailey.
Here.
Thank you for your note about quizzes. Tanisha.
Here.
Shelby.
Here.
Colton.
Here.
Tony.
Here.
Colin.
Here.
Stacy.
Present.
Ryan.
Here.
Chandretta. Stormy.
Here.
Samantha. Casey. Rolanda.
Here.
Sheldon.
Here.
Marquavius. And James.
Here.
All right, our newcomers are
Parker.
sorry,
Chelsea Parker.
Chelsea. Okay. So today, okay, about the test. One, I'm providing the Scantron. Please bring a pencil. Please bring a pencil to mark off the Scantron with. I don't have pencils. Please bring a calculator. Right? And if you desire, bring your one sheet of notes. Okay?
Front and back, like we can do something.
So, one thing you may find is if you don't know the material, those notes don't help as much as you think they would. If you do know the material, the notes help a lot. Right? So, that's why a lot of profs are like, oh, you let them bring in notes. I'm like, yeah, but if they don't know what the material is, the notes don't help nearly as much as you might think they would. They still need to know the material. All right, today we're talking about the star nearest to the Earth. And what is that?
The sun.
The sun. That's right. The sun. I can find a. What is that? There we go. All right. Warm up, warm up. So, the sun is this big, really big ball of gas, right? Mostly hydrogen because it's pretty young. And it is the source of sunlight, right? It's the source of the warmth that keeps our plant life running. It's the source of the warmth that keeps us running. And so it is converting hydrogen into helium. We'll get to exactly how that works, but it's converting hydrogen into helium. And this produces energy equivalent to 100 nuclear bombs, right? And what keeps it from just, boom, blowing us away? Gravity, right? It's also gravity that's actually causing it to be a nuclear furnace, right? Gravity is what's driving it at the end. So, its radius, 100 times that of the Earth. Its mass, 300,000 times that of the Earth, right? Its mass is a lot higher than ours. And we have been trying to figure it out for a long time. There are a lot of different observational techniques that have gone into piecing together exactly how the sun works. This, I believe, is Mercury against the sun. May not be Mercury. It looks a little big for Mercury. That may be Venus. Next summer, and of course it happens right between the two summer sessions. Next summer, Mercury will transit the sun. And so if we get the right filters and everything in place for our telescope, we can actually watch Mercury as it goes across the face of the sun. So that's a pretty cool thing to see. It doesn't happen as often as you might think. All right, so the sun is 1 AU away, about 150 million kilometers, and it is, its angular size is half a degree, right? So that makes its diameter about 1.4 million kilometers. This is a picture of the corona. This is gas. We'll get to this later, but this is gas following magnetic field lines. All right, so again, surface gravity on the sun is about 30 times what it is here. And the surface temperature, based on its color and Wayne's law, is about 57 to 80 Kelvin, right? That's about the surface temperature of the sun. Let's see, pretty much everything melts by the time you get to 57 to 80 Kelvin. Pretty sure everything melts by the time you get there. It is, from our observations and from our theoretical models, it's a gas all the way through. It does not, like Jupiter and Saturn and Uranus and Neptune, have any sort of rocky iron core in the very middle, right? It's a gas all the way. Amount of solar energy that reaches the Earth is 4 times 10 to the 26th watts. Right? That's like 4 times 10 to the 24th 100-watt light bulbs. That's a lot of energy reaching the Earth every day. And it has plenty of hydrogen left still. 71% hydrogen, 27% helium. All right? The other bit on this slide, the surface temperature of the sun is a little under 6,000 Kelvin, but the core temperature down in the middle we estimate is 15 million Kelvin. 15 million Kelvin. That's why even though the pressure is immense, the core of the sun is still a gas. There are several parts. Some of them you can observe during an eclipse, if you have the right equipment, there's the corona out here, there's the chromosphere, then there's the surface, which has sunspots. There are some things, when something comes out and loops back in with the sun, we call that a prominence. There's the zone here on the sun that's convection. That convection zone is where the gas, if you imagine, when you boil soup or something like that, you can see the soup coming up and going back down and coming up and going back down, right? As convection carries the heat to the top and then it cools and falls back in. And that's what's happening in this zone. Gases get heated up, they come to the top, they cool down because they then can release energy in the form of sunlight, right? And then they head back down and they heat up, and there's just this constant boiling, right? One way to think of it as convection zone is boiling. It's constantly boiling in that area. Material is constantly moving around, carrying heat from the inside and out to us to use as sunlight. So this surface is the only part where we actually see anything. Underneath, it's actually pretty dense, right? And then there's this area where the heat's radiating out to the convection zone, and then in the very center of the core at 15 million K. And I don't know if you saw it down here, but just for comparison, here's the size of the Earth, right? There's been this big, and the sun is quite a bit larger. So the light we see, or the photons we see, all get created up here at the surface, right? On this photosphere, which is just the very surface. And it's only on the surface that the light we see is created, because anytime a photon is created anywhere else in the sun, it's so dense that that photon hits something else and gets absorbed right away. It actually takes a very long time for energy created here to work its way out to the surface. All right, so everything below the photosphere is constantly absorbing and re-emitting photons. It's only once they make it out to the surface that they escape the sun. At its surface, the density of the sun is about the same as water, 1 gram per cubic centimeter. You have to remember, though, that's not water, that's hydrogen gas, right? So the hydrogen gas is compressed enough that it has about the same density as water. And as you go deeper and deeper, in, the density goes up to 150 grams per cubic centimeter. Temperature starts at around 6 Kelvin, goes up to 15 million Kelvin. Right. The radiative zone is the area where energy is constantly just flowing straight out, right? The convection zone, energy is going in and out and in and out, and things are moving around. The radiative zone, energy is a steady flow of energy out, and photons going out. And this is the, and then this is all the energy is coming from the core. And it's at the core where the actual nuclear reaction is taking place. All right? The rest of this is a shell around the nuclear furnace, which is at the core. And it's at the core where gravity is high enough that the protons get pressed together. we estimate that if a photon gets created here in the core, that it actually takes about 16 million years for that energy to make it out to the surface and escape. Okay. It's because photon travels and gets absorbed, gets emitted again, gets absorbed, gets emitted again, gets absorbed, gets emitted and absorbed, emitted and absorbed. Right? It's a very frustrated little photon. It never gets to go far. Right? It's kind of like, I can't remember his name right now. Running back for the Chicago Bears came from Alcorn. Walter Payton. Right? Over his career, he ran 11 miles, but he got knocked down on average every 3 feet. Right? So that's what's happening with these photons. It takes them 16 million years to get out. Why? Because they keep getting absorbed again. Then once they make it out of the convection zone, then they manage to heat up some material that floats to the top, and they get emitted out as light that we see. All right, so in the convection zone, one of the reasons we know that it's this boiling, roiling mass of gas is because we can actually see that. Right? We can actually see if we take if we have the right filters on our telescopes and looking close, we can see where the surface is just constantly boiling. Right? You can see this roiling motion that's happening on the surface, and the bright zones are where hot gas is coming up, and the dark areas where it comes up and then starts flowing back down. Right? So the dark area is cooler, the bright area is hotter. So when you're looking at a pot of soup boiling on the stove, the bubble, the middle of the bubble coming up is the hottest, and then it starts going down around the edges from there. It's the same thing happening here. During an eclipse, you can see the chromosphere. Right? You can see the chromosphere, and you can see the corona. So once you leave the surface of the sun, the density decreases steadily, just like the density of our atmosphere, until it kind of merges with space. Right? The odd thing is, as the density goes down, the gases in the atmosphere around the sun do exactly what you would expect. They cool off. Until you get out into the corona, where you're out beyond, out into really thin, talking a few atoms per cubic meter. When you get out there, the temperature actually goes up. Now, here's the thing you have to keep in mind about temperature. Temperature is a measure of how fast molecules are moving. Right? Heat is a measure of how much energy you have in something. So even out here in the corona, even though the temperature is really high, there's not a lot of heat because there are so few molecules. There's more heat in a boiling pot of water, which is a lot cooler, but it has a whole bunch of molecules in it, than there is in the same volume out in the corona, even though the temperature may be several million Kelvin. Right? Temperature is a measure of how fast the molecules are moving. Heat is a measure of how much total energy you have. So if you have one molecule moving really fast, that doesn't really make up for having billions and billions of molecules moving not so fast. Right? It's just a matter of, you've got a whole, in a pot of water, you've got billions and billions of molecules. Doesn't matter if they're not moving nearly as fast. You've got so many more of them that the total energy they have is much more than the energy density out in the corona. We still don't have a great explanation for why molecules in the corona of the sun reach these really intense temperatures. We think it has to do with the magnetic field, but this also happens around Jupiter and Saturn. So the magnetic fields from Jupiter and Saturn also create, far out from the planet, a zone where there are molecules with really high energy. The chromosphere, right? The chromosphere is this thin little red area around the sun that that is mostly, it's red, mostly because of what's called the hydrogen alpha line. All right? So this is the lowest energy photon that hydrogen emits. Hydrogen alpha line. Millions of thin columns called spicules. Each is a jet of hot gas coming out. Right? So the chromosphere is this hot, all these jets, it's kind of like the steam coming off of the boiling water. Right? These hot jets coming up, it's hydrogen, it's emitting on the hydrogen alpha line. Once they emit, those atoms have cooled off some. They're gravitationally still attracted to the sun. They end up back on the surface. The corona can extend out a very long way. And, you know, it's actually pretty amazing. The sun and the moon are both about the same angular size. So when we get a total solar eclipse, we get to take pictures like this, right? You know, if we were on Mars, when one of Mars's moons goes across the sun, it's just a dot going across the sun. It doesn't come anywhere close to covering it enough to do this kind of stuff. So the corona, you can see, really extends out quite a ways into space. You can also see it's not like an atmosphere, right? That just surrounds the sun. It's got structure in it where things have gone off in different directions. Okay. So, how does the sun work? We have gravity, all right? You got to remember, the sun is 300,000 times more massive than the Earth, right? So we've got a lot of gravity to deal with, and gravity is pulling things in, and the pressure from all the gases in the middle heating up is pushing things out. And so this balances out, right? The sun is doing this balancing act where the pressure from the heat, heating up the gases on the interior, is holding back the gases and keeping them from completely collapsing. Pressure is nothing other than gas molecules and atoms bouncing off of things, right? If you can imagine if we had a bunch of racquetballs and we all threw them at that wall, right? That wall is going to feel pressure from all those racquetballs. Now, if we have hotter racquetballs, that means we throw them harder, right? Or we have more racquetballs and we're throwing a whole bunch. There's more pressure. So pressure is just due to the motion of the atoms. There is a net loss of energy from the sun, from all those photons going out. And here, if the sun were made of coal, it would only last a few thousand years and that'd be it, right? It's because it's using a much more efficient energy source, which is nuclear reactions. It was back in the early 1900s where Einstein proposed that mass could become energy, right? And that's what he's really saying in this equation, E equals mc squared, that the amount of energy in a particular amount of mass can be calculated. And what's happening in the sun is mass is becoming energy. And what's happening in the sun in particular is called fusion, right? The bombs we dropped on Hiroshima and Nagasaki were fission bombs. They were from large atoms, uranium atoms, falling apart. And when they fall apart, they give off some energy, converting some mass over into energy. Well, what the sun runs off is fusion, which is putting atoms together. And we actually get much more energy out of putting atoms together than we do by taking them apart. So it begins with protons and neutrons. So this is a hydrogen nucleus. This is a standard hydrogen nucleus, just one proton. And there's deuterium, which has a neutron added, and tritium, which has two neutron added, which is not on here. Then there's helium-3, which is two protons and a neutron. And then there's helium-4. Helium-4 is the nucleus of a standard helium atom that we find in nature. This is the nucleus of a standard hydrogen atom that we find in nature. These also occur in nature, but they are rarer because they decay. So what happens as the sun's gravity takes effect here? Well, basically the sun gets enough gravity, the gravitational pressure is enough to force two protons together. Right? That takes a lot of pressure because the protons are both positively charged and they repel each other. Right? They are actively repelling each other, but the gravitational pressure becomes so great they're forced together. When they're forced together, in order to drop into a lower energy state, one of the things that happens is one of them converts over into a neutron. And they do that by emitting a positron, which is the opposite of an electron, an anti-electron. Positron and electron meet, they turn into a photon, they annihilate each other. All right? And something called a neutrino. We'll talk about neutrinos in just a minute, because there was a Nobel Prize given for work on neutrinos this year, just a few days ago. So, all right, so two protons get forced together to create deuterium, and then a proton gets forced into with deuterium to create a helium-3. When this happens, we emit a gamma ray. And that's the beginning of getting energy out of the sun, that gamma ray. Okay. Then, a couple helium-3 atoms get forced together. In order to drop back into a lower energy state, they kick a couple of protons out and form a stable helium-4 nucleus. Okay. And again, we get more energy out of it than went into. The key thing is, when the sun pushes these things together, we get more energy out of, the sun gets more energy out of that than went into pushing it together. Because some of the mass was converted into energy. Neutrinos are cool. If you're a physics geek, neutrinos are cool. Neutrinos have almost no mass. Almost none. And while I've been talking, trillions and trillions and trillions of neutrinos have passed through you. Right? They have almost no mass. They're not very friendly. They don't interact with anything much at all. If you wanted to have a 50% chance of getting one to stop, you need a light year of lead in its way. Right? A light year of lead would be enough to give you a 50% chance of getting one to stop. Because they just do not interact much at all. But we can still study them. Why? Because we don't need for them to react very often if there are a trillion going through us every second. Right? So one of the big mysteries that arose a few decades ago, right? Time passes, a few decades ago, one of the big mysteries that arose was that these neutrinos, these electron neutrinos that come out of this interaction, when we started looking to see how many are coming from the sun, we found out that only a third as many were coming from the sun as should be coming from the sun. And the Nobel Prize was recently given for the gentleman that proposed a mechanism where this neutrino, as it travels along, can change flavor. That's what we call it in physics, change flavor from an electron neutrino to a muon neutrino or a tau neutrino. Okay, so there are more energetic states, or more energetic versions of all the particles we know, and it can convert into these other families or these other flavors. And that explained, these guys were able to explain, when we were finally able to get the experimental experiments done to show that neutrinos actually manage to change types along the way. We did this by, one, so they're really hard to see, they're really hard to do anything with. And so what you have to do is create, it's kind of like I want to hear, if you imagine, we want to hear a flea jump in this room. Right? If we wanted to hear a flea jump in this room, we would have to make this room very, very quiet. Right? And then put in really sensitive microphones. If we made this room just absolutely quiet and put in really sensitive microphones, we might actually be able to hear a flea jump. That was the kind of equivalent experiment they had to do to detect neutrinos. So the first thing they did was they buried it deep underground to isolate it from all kinds of other things, right? So you need to isolate it from everything you can possibly isolate it with, and it's also very big. I think most of the neutrino experiments that have been done, you could almost fit this building inside of it, right? Because you want a very big space. And then you use phototubes and water, and you watch in absolute darkness, which is equivalent to us having this room being absolutely silent. You watch in absolute darkness for little flashes that are the neutrinos interacting with the water. You get just a little flash. And you can measure the energy in that flash, and the electron neutrinos, the muon neutrinos, and the tau neutrinos all interact slightly differently. They also did this was my favorite, was sort of, they said we need a big block of crystal clear ice to do our experiment. And so they actually went to Antarctica and just dug holes straight down and buried their detectors in the ice about a mile down. So they had a big area that was just pure crystal clear ice. So we're at a solar astronomy observation on neutrinos has led to a major revision. Right? It's always exciting when we find out we're wrong. Physics is one of those few disciplines where everybody gets excited about finding out we were wrong. We really get excited about it. It's really cool. All right. The other thing we can do is, by watching the surface of the sun very carefully, we can watch waves, sound waves, right? Sound waves propagate through the sun. Now, these are not waves you would hear, right? It's not the sun saying, hey, good morning. No. This is big waves in the sun where the gas is flowing. We can watch this happen. We can do it from temperature and density profiles and see how that all happens. You can actually see in the sun it occasionally gets into certain resonant modes. Right, so you can see all of this sound, and this is sound. Sound is just the movement of gases. This is sound doing this. And then, some of the prettier things that give your cellular provider nightmares, right? Sometimes the magnetic field lines from the sun manage to penetrate the surface and they come out and they loop back down, and when they do that, gases begin to flow, right? Gases begin to flow along those magnetic field lines, and we get these huge prominences. When I say huge, I think the Earth on this picture would be about that big, right? I mean, massive, massive prominences. Those prominences happen because charged particles, which is what's making up the sun, charged gases, when they're moving, they tend to follow along and spiral along the magnetic field lines. This is why we have our aurora borealis here, because the Earth's magnetic field lines come in there, and so charged particles that hit the Earth tend to turn and follow those magnetic field lines to the North Pole or to the South Pole. Sunspot, this is a, calling them dark spots is kind of a misnomer, right? They are not as bright as the sun surface next to them. When we're looking at sunspots, if you were to look at, if the sun if the sun suddenly just went to the same brightness as one of the dark spots on the sun, right? You would still lose your vision if you stared at it. So it's not that they're dark, they're just not nearly as bright as the surface next to them. Right? So if I had two flashlights, one was really bright and one was just kind of bright, and shined them both at you, the one that was just kind of bright wouldn't look very bright. But if I had just the one that was kind of bright shining on you, it would look bright. Right?
Yeah.
That's why the dark spots look dark whenever we manage to get things dim enough to take a picture of them. They're cooler, 4,500 Kelvin versus 6,000 Kelvin. And this is where the magnetic field lines are popping up out of the surface. Right? So magnetic field lines going along, come up, come back down, gases come up, follow those along, and head back down into the photosphere. Here's a really good prominence with the Earth for comparison, right? So sometimes just really gigantic structures occur. And we have, for a long time, for a variety of reasons, started watching the sun instead of just observe it all the time. sunspots also give rise to solar flares, and solar flares are where material actually gets ejected from the sun. All right? And this is the source of a lot of the material that hits the earth in terms of the solar wind, right? Solar flares are ejecting material all the time. On occasion, you'll hear them warn, because we'll see the flare. So the light from the flare travels how fast? How fast does the light from the flare travel? Speed of light, right? 3 times 10 to the 8th meters per second. So when we see a flare, it happened about, what, 9 minutes ago? All right? So one of the reasons we watch the sun is we see a big flare that happens where it's sort of coming out in our direction, right? And we see that in a few minutes. Well, it's going to be about 3 days before all the particles that were ejected from the sun reach our orbit. So we watch the sun because we now have 3 days to think about, is this going to be enough material to cause a problem? It has on occasion caused problems with communication satellites. Right? So you may have heard on occasion, hey, there's a solar flare, satellites may be problematic on Tuesday, or Wednesday, or Thursday, right? So sometimes we get a little warning, hey, a bunch of stuff is headed our way. You might want to be aware of that and know that we might lose communications for a little bit. Sometimes, and so far we've not had one of these come out towards us, but sometimes you get a really massive ejection of material, right? And we do worry about one that big because it probably would disrupt communications. And this is a picture of the Aurora Borealis, which is where those particles are hitting the atmosphere on Earth and causing the gases in our atmosphere to glow. All right. So, what the last slide was trying to say is, when this material gets ejected out and it cools off the sun here, right? It's actually heating up everything up above it, because that's where some of the energy went, into heating up the chromosphere, into heating up the corona. And that may be one of the reasons we keep pumping energy into corona, and those atoms become very energetic, very high temperature. So, the solar wind, all of that material coming out, is not a lot of material. It's a few atoms per cubic centimeter. Right? Just a few. Compared to most material like this has about 10 to the 23rd atoms per cubic centimeter. Right? 10 to the 23rd is a big number. So ordinary material has about 10 to the 23rd to a cubic centimeter. Solar wind, just a few atoms, right? 1, 2, 3, 4, 5 atoms per cubic centimeter. But they are booking along 500 kilometers per second. The solar cycle, how many of you have heard of the solar cycle before? Sun getting hotter and cooler and hotter and cooler and hotter and cooler. Now, it does this on roughly 11-year increments, roughly. And we see this because about every 11 years, and it's not like clockwork, it's sometimes 6, sometimes 16, but about every 11 years, we see a rise in sunspot activity, and then we see it die back down. Climate patterns that we have, to some extent, follow the solar cycle. Solar cycle is tied to this. So if you were able to stand on the sun at the equator, you would go all the way around in just 25 days. Right? All the way around in just 25 days. But if you're further away from the equator, you are taking 30 days to go around. So the middle of the sun is going around faster than the top and bottom. Right? And can you imagine if the middle of the earth was going around faster? And you're like, oh, the Bahamas are closed this week. Oh, there they go. Oh, now they're back, right?